Now let me define this group homomorphism. Consider two groups G under the binary operation dot and another group G prime under the binary operation star. Note that this G may be equal to G prime or may not. If G is equal to G prime, then they will have the same binary operation. If G and G prime are different groups, they may have different binary operations, say dot and star here. Now we define this, we consider these two groups. Now a mapping F defined from this group G to another group G prime is said to be a homomorphism if it satisfies this condition. Fx dot y is equal to Fx star Fy. Why I am taking this one, the binary operation dot here, because x and y are elements of G. So the binary operation between the elements of G must be this dot. So Fx dot y should be equal to Fx star Fy, because when you apply F on x, then this will be an element of G prime. Similarly, Fy also will be an element of G prime. That's why we have the binary operation between these two elements now will be star, which is an binary operation in G prime. For example, so if you can show this condition that Fx dot y is equal to Fx star Fy, then in that case we can conclude that the mapping F defined from this group to this group is a group homomorphism. So now let us consider this example so that it will be more clear to you. Take G is equal to set of integers and then G under the ordinary binary plus, which is equal to set under the binary operation plus. This forms a group. And then take another group G prime. G prime contains this element, or consists this element 1 and minus 1. Then G prime under the multiplication, that is the usual multiplication. So this also forms a group. You can just check from this table that this is the binary operation. Then these are the two elements 1 and minus 1. Then from here you can see that it satisfies all the group axioms. Now let us show that this is a group homomorphism. So how will you define a mapping theta defined from G to G prime? You define it as theta of M is equal, because M here is that set only, set of integers. Here G prime is that set which contains plus 1 and minus 1. So define it in this way, theta M, where M is an integer, as 1 if M is even and equal to minus 1 if N is odd. Okay. So we define this mapping in this way, theta M is equal to 1 if M is even and minus 1 if N is odd. Now let us show that it satisfies this property. Let Mn belong to set. Now what is theta of M plus N? Because the binary operation in set is plus only, so it will be theta M plus N. This is equal to what? Now case 1, let us take this case 1. Mn are even, and we know that the sum of even integer is even again, so M plus N will be even. So this will be, it will be equal to 1. And now let us find out what is theta M separately. M is even, so it will be 1 again. And what is theta N? Again, N is even, so this will be 1. Now what is theta M plus N? This is 1, and this is same as theta M into theta N, which is equal to 1 into 1 equal to 1. Because the binary operation theta M is an element of G prime. So the binary operation here is that multiplication. So it is between them, it will be the multiplication. So theta M into theta N is equal to 1 again. So therefore this gives you theta M plus N is equal to theta M into theta N. Now let us consider case 2. M, N are odd. Now we know the sum of two odd integers will be uneven integers. So therefore in this case, let us see what is theta M plus N. Because M is odd, N is odd, M plus N will be even. So by definition, it must be equal to 1. And then what is theta M separately? M is odd, so it will be minus 1. And what is theta N? Again, N is odd, it is minus 1. Now what is theta of M plus, what is theta of M into theta N? This is equal to minus 1 into minus 1, which is equal to 1, which is same thing as theta of M plus N. So for case 2 also it is true that if M and N are odd, then theta M plus N is same as theta M into theta N. Now let us come to the third case, this one. case 3 is m is even, n is odd. Then in this case, m plus n will remain as odd only. So what is theta of m plus n? M plus n is odd. So by definition, if m is even, if m is odd, then it is defined as minus 1. And then what is theta m separately? M is even, will be minus 1. And what is theta n? Because n is odd, so it will be defined as minus 1. Here please correct, this one is plus only. This is plus 1 and theta n is minus 1. So what is theta m into theta n? This is called 1 into minus 1, which is minus 1. So which means that theta of m plus n is same thing as theta m into theta n. So now from all the three cases, we can conclude that this theta defined from set of integers to the set to this group, which consists only two elements 1 and minus 1 under the binary operation multiplication, is a homomorphism because it satisfies this property fx dot y is fx star fy, where dot here is that addition and where star here is that multiplication. Now let me come to the next one. Epimorphism. Now what is epimorphism? So you consider again this group G and the binary operation dot and another group G prime and the binary operation star. So f defined from G to G prime is said to be an epimorphism if f is a homomorphism, that is fx dot y should be the same as fx star f of y. And number 2 condition, the extra condition here is that f must be on 2. That means every element of G prime must have a pre-image in G. So now let us consider the same example. Take G is equal to set and G prime is equal to set 1 and minus 1. Then this becomes a group under the ordinary addition, and this G prime under the binary operation multiplication becomes a group. So again the same thing, define f from z to z minus 1 and minus 1 as fn is if n is even and fn is minus 1 if n is odd. So in the just now we have seen that f is a homomorphism. So it already satisfied the first property. Now what about f is on 2? Number 2, f is on 2 in this case. Why? Because these elements of G prime are 1 and minus 1. And we have seen that f is on 2 since for any x belong to G prime, there exists for every y belong to G prime, there exists an x belong to z, such that y is equal to f of x. Because what is y? When y is equal to 1, then we get x is even. So that means for y is equal to 1, there exists x is equal to m, an even number, such that 1 is equal to f of m. And for y is equal to minus 1, which belongs to G prime, there exists x is equal to this one, odd integer, such that minus 1 is equal to f of x. So therefore in this case we can see that every element of G prime has a pre-image in set. Therefore this homomorphism f defined from set to set 1 minus 1 is not only a homomorphism but it is also on 2. Therefore we can conclude that it is an epimorphism. Now the next one is this one, monomorphism. F defined from G to G prime, the same thing only, is said to be a monomorphism if f is a homomorphism, that is f of x dot y is same as fx star f of y. And number 2 condition now here is instead of on 2 it is f must be 1 1. So take G is equal to set and G prime is equal to 2 set. Now you define a mapping f from G to G prime as fx is equal to 2x for x belongs to set. Now this one is a homomorphism. Let x and y belong to set. Then what is f of x plus y? It is equal to f, by definition it is 2 times of x plus y, which is 2x plus 2y. Let us find separately what is fx. Fx is equal to 2x. F of y also by definition it is 2y. So this implies that f of x plus y is equal to 2x plus 2y, which is same thing as fx plus f of y. So it means that f is a homomorphism. Now to show that f is on 2, let me just, or not on 2, it is 1, 1. So let x and y belongs to G such that fx is equal to f of y. So if assume this one, suppose fx is equal to f of y. If you can prove that x is equal to y, then we can conclude that f is 1, 1. So fx is equal to fy implies that 2x is equal to 2y. And this implies that x is equal to y. So it means that f is 1, 1. So therefore, this is an example of a monomorphism. Now let me define this definition of isomorphism. What is isomorphism? A mapping f defined from G to G prime is said to be an isomorphism if number 1, f is homomorphism, f is on 2 and f is 1, 1. That means if it satisfies all the 3 conditions, that is homomorphism, on 2 and 1, 1, then in that case the mapping f from G to G prime is said to be an isomorphism. And the simplest example here is this one only, f defined from set to 2Z defined by fx is equal to 2x. We have seen that this is a homomorphism just now and it is 1, 1. Now only thing that is left now is to show that f is on 2. F is on 2. Since for any y belong to 2Z, y must be uniform, because what is 2Z? 2Z contain all multiples of 2. So it will be uniform 2m, where m belong to Z. So y is equal to 2m. So that there exists m belong to Z. That means there exists m belong to this one, because m is an integer, such that y is equal to f of m. That is 2m is equal to f of m. That means every even integer here has every element here has a pre-imaging set. So this implies that f is on 2. Since f is homomorphism, f is 1, 1 and f is on 2. So therefore the mapping f defined from set to 2Z under the binary operation plus here also, this is plus here, is an isomorphism. So this is a simple example of a group isomorphism. And the last one is this one, the definition of automorphism. Automorphism is nothing but it is an isomorphism, but here instead of defining a mapping f from G to another group G prime, it should be a mapping f defined from a group G to itself only. Okay, so if the binary operation here is dot, this also will be dot, because these two groups must be the same. So a mapping f defined from a group G to itself is called an automorphism if number 1, f is homomorphism as usual, f is on 2, and number 3, f is 1, 1. So automorphism is nothing but it is an isomorphism, but the only condition, the only difference between isomorphism is that the mapping here f, it must be defined from a group G to itself only. So the simplest example here will be this one, f defined from set and addition to itself, set and addition defined by fx is equal to x. This is a homomorphism. You can check that fx plus y is same as fx plus fy. Similarly, it is 1, 1 and also on 2. Therefore, these are the definition of all group homomorphisms, so that in the next class I can prove some theorems related to group homomorphisms. So you just go through it. In case if it is not clear, you please let me know.